Hello, everyone. So today we're going to continue talking about some beautiful theorems that we can prove with intersection theory. So now, in this lecture, we will talk about the Poncare Hop Theorem and then the Lefschetz fixed point theorem. But let's start with the Poncare Hop. So the Poncare Hop theorem is a theorem about vector fields. So when you have a vector field on a manifold, you can say things about the zeros of the vector field. So when zeros exist, then actually there's a very nice formula for sort of the number of zeros as a function of the Euler characteristic. So this will basically say that the number of zeros counted with multiplicity is equal to the Euler characteristic. So that's what the Poncare Hop theorem says. So now we'll see, first of all, I have to make sense of all of that. So we needed a few definitions, and then we'll prove the theorem. And I have to say what the Euler characteristic is, in case you don't know. So let's do that. So we are going to fix an oriented, so let X be an oriented manifold, so without boundary. And let V be a vector field. So remember what that means. That just means that, so V is a section. This is the section, the set of sections of the tangent bundle. Okay, so that means that for each X in X, Vx is an element of the tangent space above X, and this V is smooth. Okay. So now we can choose a chart, an oriented chart, near. So before doing that, now we fix a zero. We take a zero of the vector field. So let B be such that Vp is equal to 0. So take a 0, and suppose it's isolated. Okay, so suppose there exists an open set U containing P such that P is the only 0 in U. So such that Vx is 0 for X in U, if and only if X equals P. Okay, so that means that this vector field has a 0 at P, and there's a neighborhood with no other zeros. Okay, so that means it's an isolated 0. Okay, so for such a 0 of the vector field, we're going to define an index. Okay, so this is kind of the multiplicity of the 0. But actually, unlike zeros of polynomials, a 0 of a vector field, it doesn't only come with a multiplicity, but it can also come with a sign. So that's what we're going to see now. So now we'll define the index of the vector field. We usually write it like this. So this is the index of the 0 of the vector field. So it's the index of V at P. Okay. So this is defined as follows. So first of all, we choose a chart. So choose a chart, an oriented chart, phi from U in Rn. And this U is at most this U. So I'm kind of using the same U. So potentially the same U, but you might have to shrink it a little bit. But in any case, I want the vector field to still have only P as a 0 inside of U. So u potentially smaller, u may be smaller than the original u, but that's okay. And to simplify matters, we suppose that u is really like the image of u is a ball. So to simplify, we suppose that this is this, and that phi of u is some ball. Yeah, just to make it, I don't know, ball of radius epsilon. Okay, I just want to make sure it's contractible. But anyway, so now in particular, we can actually, so this induces, the chart induces a map that basically, that trivializes the tangent bundle over here. So this, I actually will choose the map that just that takes this to Rn. So, basically the map would, let me write the whole thing, and then why not? So there's this phi bar that takes txu to u times Rn. So this is the induced trivialization, and then later I will compose the projection to the second factor. Okay, so if you compose this to the projection to the second factor, then what happens is you can see your vector field as a map from u to Rn. So after basically if you look at your vector field and you compose it with phi inverse, and you compose it with phi bar, and then you just project it to Rn, then this will be a map that goes from this ball into Rn. Okay? So this is like the local expression of your vector field. So you can call this V bar. So you define and notice that the only zero of this map is really 0. So outside of 0, you get a non-zero vector here. Okay, because you're a 0 of the vector field, if and only if you're taken to 0 on the second coordinate here. Yeah. All right. So that means that in particular on the boundary of this ball, this function isn't 0. That's true for every ball, actually. You can even shrink the ball if you want. But anyway, now you can define the index of V at the point P to be the winding number of this vector field V restricted to the boundary of the ball, comma 0. Okay? So this winding number, which is the same thing as a degree of normal V divided by its norm at this, on this sphere. Okay? So that's the index. Okay, so now I can state the Poncare Hop Theorem. And before we prove it, of course, we're going to do many examples, but I think it's worth stating the theorem at this point. So now we know what it means for what the index of an isolated 0 of a vector field is. So the Poncare Hop Theorem says the following thing. So suppose all zeros, I mean, we have this set up, so X is an oriented manifold with no boundary. And we take a vector field, and suppose that all the zeros of V are isolated. Then the sum of these indices, no, I actually need one more condition. So I have to suppose that the manifold is compact. So suppose that all the zeros of V are isolated, and X is compact. Then the sum of these indices for all zeros, is equal to the Euler characteristic of x. Okay? So you might ask, what is the Euler characteristic? I think everybody has heard of the Euler characteristic and has seen it defined in some cases, at least. So, what I'm going to do now is I'm going to define the Euler characteristic, which is actually easy to do with intersection theory. And I'll give you some examples of this before we actually we prove the theorem. Okay. Well, any questions so far? No. So anyway, how can we define the Euler characteristic? It's very simple. So at least for an oriented, if X is an oriented and compact manifold without boundary, then we can look at the diagonal as a submanifold of X times X. So the diagonal, is the set of points x, x inside of X times X. And that is a submanifold of here. And it has, given an orientation of X, this has a natural orientation. Okay? So then this guy is an oriented submanifold here. So then, and the codimension of this, the dimension and the codimension are the same. They're half the dimension of X times X. So the dimension of delta is equal to the dimension of X, which is half the dimension of X times X. So that means that we can actually look at the intersection number of delta with itself. So there's no restriction. When you look at the intersection number of two oriented submanifolds, if they have complementary dimensions, if the sum of the dimensions is the total dimension, then you can look at the intersection number. And they don't have to be transverse because we show that if two manifolds don't intersect transversely, or if a map and a manifold don't intersect transversely, then you can perturb the map, and that's well defined. Okay, so that means that you can talk about the intersection number of a manifold with itself. Because the sum of the dimensions adds up to the dimension of the total space. And because everything's oriented, this is an actual number. This is a number in Z. Okay? And I mean, it is a number in Z also because it's compact. So you have to have sort of the domain compact. You have to have so basically so that you have a finite count there. But it's true. This fits into the theory that we developed. So we have basically one of the manifolds is compact, the other one is closed as a submanifold, so then they have a finite number of intersections. I mean, this number is well defined. Okay, and then one more time, how did we define it in terms of our theory? When we have two submanifolds, the intersection number of the two is the intersection number of the inclusion function with the other one. And of course, the inclusion function is not transverse to the diagonal, but you can perturb it so that it is transverse. So the idea is like in the graph, I'm going to draw it like this. So what does it mean to look at the self-intersection? So basically, you take you take the inclusion of the diagonal into X times X, and then you look at the diagonal itself, and then you perturb the inclusion. And then you count the intersections with signs. Okay, so that's what this term is. And anyway, that's the definition in differential topology. That's the definition of the Euler characteristic. Okay, so that's what it is. And I guess now if you believe that this makes any sense, you're like, okay, I still need to see how this fits into my previous understanding of the Euler characteristic, and I'll get to that today, a little bit later. But before, just bear with me. It doesn't really matter what this guy is, but it is a topological invariant of X, and it has nothing to do with the vector field, V. So in particular, you could just take this Poncare Hop Theorem for now as saying, this number of zeros, when you take into the index of the zero, as some kind of weight of the zero, this number here, the sum of these numbers is an invariant of the manifold. It's a topological invariant. So if you believe in this theorem, now you can actually compute a bunch of Euler characteristics. Because there are some manifolds. You can start with surfaces, and you can easily construct vector fields on them. And then you can compute these numbers. OK? So let's look at some examples now. So let's look at the case n equals 2, which is kind of interesting enough and low enough dimension that we can draw pictures and understand what's going on. So if you have a zero of a vector field, there are basically three kinds, well, there are several kinds, but let's start with the three simplest kinds of zeros. So the first one is called a source, and then a saddle, and then a sink. I think probably most of you have seen this in some ODE class or maybe a dynamical systems class. So a source is a vector field, is a zero that looks like this. A saddle is a vector field that looks like this. And a sink is a vector field that looks like this. OK. So we can look at these, and we can compute the indices. So do you have a guess of what the indices of these vector fields are, just by looking at the picture? What are the indices of these zeros? One for the three? That's right. Yeah. So, what's your name? Gabriel, yeah. Gabriel is saying that, he thinks it's 1 and 1 for the source and the sink, and it's -1 for the saddle. That's right. And let's see why. Basically, when I'm looking at this picture, I'm thinking of R2 with this standard orientation. So everything, like you look here, has a standard orientation. So what you do is you have to look at a little sphere around 0, which is a circle. And you have to look at the vector field restricted to that as a map from the circle to the circle. Or you start as a map from the circle to R2 minus the origin and divide by the norm. So when you look at this, this basically looks like the identity map from S1 to S1. I mean, at least in this realization, it is the identity map. Maybe there are more general sources, and you have to kind of make sure that use some diffeomorphism to get to this. But in this particular picture, it really is the identity map, at least what I drew here. OK, so this is the identity map. Z goes to Z. And I mean, of course, this has degree equals 1. OK, so that means that the index of this vector field, this point here, is 1, plus 1. Well, in this case, what do we have? Well, we have a map that, so here, basically, I point inside, then I go, and then I point outside, and I'm actually rotating like this. So I'm rotating in the opposite direction as usual. So it's not hard to see that basically you have one per image for each point. So all the points here, if you look at the map from S1 to S1, this map is still a diffeomorphism of S1. So each point has exactly one per image. But this map is actually changing the orientation. Okay? So what this map is doing, it's actually, if you think about the your z as a complex number, x plus I, y, what it's doing is it's changing the sign of the real part. It's taking x plus iy to minus x plus iy. Okay, that's what it's doing. I mean, of course, this is the nice map if I draw the picture perfectly, but it might be something that's that's homotopic to this. But okay, and if you want, you can homotope this to just z goes to z bar, just changing the complex, the imaginary part. Okay, in the sink, well, basically my map here, oh, and then I didn't finish. So this changes the orientation, but it still, every point has only one per image. So that means, that the index, the degree is -1, so this index is -1. And here, the map that I have for the sink is z goes to -z. So again, this actually preserves the orientation. So then the index is +1. Okay. All right, any questions? All right, so now if you believe in the Poncare Hop theorem, then we can use this fact to compute the Euler characteristic of surfaces. Well, let's start with a sphere. So if I look at a sphere, it's not very hard to find a vector field in the sphere with exactly 2 zeros, and one source and one sink. Okay, so basically you can look at the usual embedding of the sphere in R3, and you can look at the gradient vector field, for example, which is the standard metric. So you have the gradient vector field of the height function. So you have a 0 here, a 0 here. So if you think about this function as the function x3, and then you can look at the gradient of the function as x3 restricted to the sphere. Okay? So then this gradient, and for whatever reason, people like to think of this as like descending function. So I'm going to just put a minus sign here, but you can kind of ignore it if you want. So this will be my vector field on the sphere. And it's not hard to see that you have a global minimum and a global maximum and no other fixed points. I mean, no other zeros of this vector field. Okay. And also, it's not very hard to see that you're going to have a source. One is going to be a source, and the other one is going to be a sink. So if I put the minus sign like that, then my gradient vector field is going to do this. So you think of like water falling or something, but being restricted to the surface. Okay. So yeah. So now. Or another thing you can do, which is even simpler than that, because you can just take the vector field that points down, like sort of 0, 0, -1, and you project it to the surface. You project it to the sphere. That's going to give you, the same vector field up to scaling. Okay, so you could consider, or you could consider V to be the projection onto the sphere of 0. 0 and -1. And these vector fields are going to be a multiple of each other. Okay, anyway, so you have 2 zeros, and then you have one source and one sink. So that means that, if you apply the Poncare Hop theorem, that will tell you the Euler characteristic of the sphere is 1 + 1. So 2. Okay, so by that theorem, it's basically saying that no matter which other vector field you think about, it will have to have exactly 2 zeros counted with these multiplicities. Okay, I think that's pretty remarkable. This is a very simple vector field. You could think about a much harder one. So, like for example, let me give you the next harder one in terms of complexity. So you could think of what's called, the heart-shaped embedding of S2. So this is an S2 embedded into R3. And then you do the same thing. You look at the same kind of vector field, either one. You just either project this vector field or you look at the minus the gradient. But now you have this other embedding of S2 into R3. And then here, your vector field, so say you have, you take this other embedding of S2 into R3, and you look at the projection of the vector field 0, 0, minus 1 to the surface. And now you have 4 zeros. So you have these 4 zeros. So those are the places where the tangent space is horizontal. Okay? And then here, it's interesting because, here you do have 2 sources. And you have 1 sink. But now you have 1 saddle. So that means that the indices are going to be, so the index is going to be 1, 1, 1, and minus 1. So by the Poncare Hop Theorem, basically, I guess you can check that the Poncare Hop Theorem holds. Because when you do the sum, now it tells you that the Euler characteristic of the sphere, which you kind of already know it's 2, is equal to 1 plus 1 minus 1 plus 1. Okay? And basically any other vector field you can cook up, you're still going to have this property. Okay. So now you can ask yourself, but you only gave examples of zeros of vector fields that have index plus 1 or minus 1. So can you think of something more interesting? And the answer is yes, of course, you can. And in particular, for example, you could try to think of a vector field in a sphere that has just one critical point, just one zero. So you know that, I guess maybe this is an exercise. Let me leave this as an exercise. Find a vector field on the sphere with a unique 0. So you know that by the Poncare Hop Theorem, if there is a unique 0, then it had better have index 2. So if this does exist, then this unique, in particular, this guy, the index of the vector field at this point has to be 2. Okay? So it can't be any of these cases. So let me give you a hint. I'm actually kind of going to pretty much solve the exercise without writing all the words. So, when you think about a function of degree 2, what's the function that you think about? From S1 to S1. Z squared. Yeah, so, you think about the function z goes to z squared. So, you kind of basically take that function, z goes to z squared. And what does it look like as a vector field, if you think about it going from a little neighborhood of 0 to a little neighborhood of 0. So, as a vector field, so you look at the function z squared, which is a vector field, kind of looks like, so you go out like this, but then instead of just going like the identity, you go twice as fast. So that means, by the time you get here, you have to be like this, and then Okay, let me just draw it on the circle. So you start like this, and then here you're like this, and then here you're like this again, and then here you're like this. Okay, so then you have the behavior is basically and then somewhere here you're like this, and then here you're like this, and here you're like this, and then here you're like this. Okay. So that's basically what this vector field looks like. And you can basically write, like this, and then like this, and then there will be a direction where so let's see if I can draw the picture. Hold on. So around here, okay, let me see. One, two. Okay, anyway, I'm not going to complete the picture, but you can complete this picture if you want. And this vector field, this kind of goes from C to C. But as Z goes to infinity, as your point blows up in C, the other point blows up also. The image of Z blows up. So as norm of Z goes to infinity, norm of Z squared also goes to infinity. Which basically means you can compactify this map, at least as a continuous map, from S2 to S2. Okay? So, yeah, so in a way that's tangent. So, I actually maybe you should say, yeah. Anyway, so you can compactify this to a vector field on the whole sphere. And if you think kind of hard, you can actually maybe we can do that later today. We can kind of write down, kind of really draw this vector field. Okay, so maybe I'll leave this as an exercise for you to think about if you're bored right now, or we can do it together at the end of the class. Okay. Now we can look at higher genus surfaces. So we haven't really talked about classification of surfaces, but you might know that there are only the collection of all oriented surfaces is pretty easy. So basically, you can look at the surface, for example, that looks like this, or before that you have a torus, and then you have a surface with 2 holes, and then you can do that with as many holes as you want. And that's basically all of the compact surfaces that are oriented with no boundary. Okay, so I guess the next thing is let's look at vector fields on them and compute their Euler characteristics using the Poncare Hop Theorem. Okay, so again, I put my surface here to indicate what kind of vector field I want to look at. So here, I look at the same kind of vector field, so like the gradient minus the gradient of the height function, and then you see that you have 4 zeros. 1, 2, 3, 4. And notice it's important to put it like this. Like if you put your torus like this, then and you look at the height function, the gradient of the height function, then here what you have is you have 2 circles of zeros. Right? So because if you just look at the vertical vector field and you project it to the torus, then you're going to have 2 circles of zeros. So that's not very good because we need isolated zeros to apply the Poncare Hop Theorem. So this is not good for us. So instead we're going to look at the torus vertically. And again, by that theorem, in this case, we just have 1, -1, -1, and 1, the indices. So that means the Euler characteristic of the torus is 0. And in general, you see that if you have a surface with genus G, so with G holes, genus G, that means you have the maximum and the minimum, the maximum and the minimum of the height function. So these are 2 zeros of your vector field. And then you have 2 other zeros for each hole. So basically you have 2 plus signs, +1, and then you have 2G -1. So that means the Euler characteristic of, this would be the genus G surface, is going to be 2 minus 2G. Okay. Again, believing in the Poncare Hop Theorem. Okay, so are there any questions? Okay. So I think now we can move towards proving the Poncare Hop Theorem. So first of all, we want to, we're going to define what it means for a zero to be simple. So let V be a vector field, and P be an isolated zero. So P is said to be simple if 0 is a regular value of the map V bar over norm of V bar, where V bar is the local representation of V, where V bar was a map from sort of Sn-1 to Sn-1 is the local representation of V, or is a local representation of V. Oh, no, so sorry, that doesn't make sense. Sorry, if all points are regular values of the local representation. Oh, no. So actually, no. I think, okay, so I think now I know what I wanted to say. This is what I wanted to say. Yeah, so if 0 is a regular value of really the local representation of V before you quotient by, when you look at this as a map that goes from the ball to Rn. There we go. So we know that the P goes to 0 here, and 0 is the unique 0 of this map. because of the being isolated. But it could be, that 0 is not a regular value. And it could be a regular value. So we say that the point, the 0 is simple if basically 0 here is a regular value. Okay? So if we have, for example, if in so where this is the local representation, is a local representation. Of V. So that means, that basically the derivative, so i.e., the derivative of V bar at 0 is an isomorphism. Okay. All right, so for example, if we can see this as a complex multiplication in some chart, so if it's z, goes to z to the n, then n had better be plus 1 or minus 1. N had better be plus 1 here. Yeah. But actually, there is a way to define the one with the minus 1 too, which is basically, you can. So basically in dimension 2, this would imply that either you have the map z goes to z, or you have the map z goes to z bar. Okay, and why is that? That's basically because if dv0 is an isomorphism, then you can apply the inverse function theorem. And then you can find new coordinates in which this map at the identity, and in the neighborhood of at 0, and in the neighborhood of 0, it's just the identity. Okay, so that, if we're assuming this property, then in these new coordinates, it's kind of an exercise. There's maybe one little non-trivial step. But the exercise is that if P is simple, then then V has a local representation. In a local representation, V bar is either the identity or V bar is a reflection. And here I just, you have to be, as usual, you have to be a little careful with orientations. So if you don't care about orientations, you can always get down to the identity. But we are requiring that the charts are oriented. So if you require that charts are oriented and you just kind of get the identity always, you might have some changes of orientation. So you have to compensate. But you can always, get to a fixed, chosen, non-oriented, orientation reversing linear transformation. For example, a reflection. Okay, so my reflection here, I don't know, takes x1 to xn to minus x1 to xn. So I just flip the first one, or you can flip any of them. Okay, is that clear? Okay, so that's what it means to be simple. And clearly, if you have a vector field that's not, if you have a 0 that's not simple, you can perturb it. You can perturb the vector field, and then the simplicity condition will hold. But when you perturb the vector field, you change the zeros. Okay, so that's kind of the next thing that I want to say is so maybe observation. So if P is an isolated zero of V, then there exists a V tilde, another vector field. No, this is vector field of X. which coincides with V outside a small neighborhood of P, and such that all the zeros in, so let me call in a small neighborhood U of P, and all the zeros, such that all the zeros of V tilde in U are simple. Okay, so this is just a corollary of the Tom transversality theorem. So, apply to functions that have this form, like that are vector fields. But basically, if you have this P here, and it's an isolated zero, so that means you can perturb your vector field in this neighborhood, so that over here, all the zeros are going to be simple. So that transversality is achieved in this little neighborhood. Okay? But what you cannot guarantee is that you're going to have just one zero. So what could happen is, if this is your V, then after the perturbation, you might have a bunch of zeros that show up. And these now will be, they will all be simple. Okay? And moreover, so, maybe you can have P1, P2, etc., Pk. So these are the new zeros of V tilde. And moreover, the index of V at P will be the sum of the index of V tilde at all the Pi's. So this index has to be preserved. That's why you can think of this index as some kind of multiplicity of a zero. So sort of, you can think of it as a multiplicity of a zero because of this property that, if it's something that's not 1 or minus 1, then when you perturb, then everything is going to be plus or minus 1. Oh, I haven't quite said that, but it is true. But then you can add them up and get the index of P, the index at P. Yeah. Yes. Yeah. So this is because it's the same thing as saying, 0 is a regular value of this map. So that's the same thing as saying that when you look at V, sort of V tilde, going from this ball into the ball times Rn. So that's kind of that's when you look at the trivialization of the tangent bundle, that this is transverse to the zero section. So the zero section would be this guy, and the vector field is going here. So this condition of transversality is achieved exactly when 0 is a regular value of the projection to Rn. Okay, so you look at your bundle like this, and you have your section here, and you take a 0, but guess what Marcel is saying, is that this zero section is transverse. Sorry, the zero section is transverse to the vector field seen as a section, if and only if when you project it to the fiber, which is what I did here, that 0 is a regular value of that. Okay, that's kind of one of those calculations we've done several times, at least when you look at in charts. Okay, so one thing I kind of alluded, but I guess I forgot to say, is that if you know that P is simple, then the index is either +1 or -1. And that's because from this exercise, if P is simple, then there is a local representation on which V bar is either the identity or a reflection. And the degree of the identity is 1, and the degree of a reflection is -1. So if V is simple, I guess I should write this down. If P is simple for V, then the index of V at P is plus or -1. And the sign depends exactly on whether we have an identity or a reflection. Or in other words, it's basically, if you look at this derivative, if it's orientation preserving or orientation reversing. If you look at the linearization of the vector field at 0. So it's an isomorphism. If it has positive determinant, then it's +1. And if it has negative determinant, then it's -1. Okay? So what this is saying is that if you want to compute, one way to compute the index of a vector field at a 0 that is not simple is you can perturb it, and then you're going to have a bunch of zeros, and you can just add their indices. So this is, as I said, it's kind of like the multiplicity of a vector field, the multiplicity of a 0 of a polynomial, except that you do have to be a little bit careful because the multiplicity of polynomials are all positive. But this maybe you can think of a meromorphic function as a good example. I mean, yeah, meromorphic functions basically, if you look at their zeros on the multiplicities, it's kind of the same as these indices. The index of a 0 of a meromorphic function is the same as this index here. Okay? All right, so I think we're ready to prove the theorem. Actually, why don't I do one more example? Yeah, let's do one more example. So I want to draw a picture. I haven't prepared this, so it's a little bumpier, but I want to do this following example. So say I have two zeros. I want to build a vector field in the following way. So I want. There we go. I think now I can build the example that I was trying to build earlier. So I want to put together this with this. There you go. So this is a source and this is a sink. And I want to take that and I want to do kind of the opposite of this perturbation. I want to find a homotopy that glues the two zeros into 1 0. And this is a hint for the exercise that I told you about last time, so that I told you about earlier. So if you have a sphere and you want to construct a vector field with exactly 1 0, what you can do is you can take your standard one and you can bring the two zeros together by a homotopy, and you can collapse them and see what's happening with the sphere. So basically, this is what happens. So very nice. So there we go. So it looks like this. Great. So why do I want to do this? Because now you see that as I collapse these 2 points, what happens is, so this guy has index +1 and this guy has index +1. So as I collapse these two zeros, then actually what I get is I get a vector field with just 1 0, but that has, you expect from this calculation, from this kind of argument, that the number of, the index is preserved in this neighborhood. So now let me draw the product, the final product. So this is, I guess, the picture I was trying to draw earlier. So basically you have this direction, and then you're going to have this kind of thing. Yeah, that's what I was trying to draw earlier. There we go. OK, so there we go. So this, if you want, this is a representation of the vector field z goes to z squared. Somehow it's a little harder to see exactly on the circle. But this is what it is. So if you think about what's happening on the circle here, what is happening is that you're rotating the unit vector twice as you go along the circle once. And it's exactly, this picture is exactly modeling what's happening with the function z goes to z squared. OK, so I got the picture that I wanted to get. And I did it by collapsing. But the thing that's nice is that you can actually, if you start from this picture, you see, well, this guy has index 2. And if you perturb it, you really expect to now have two things. one of index plus 1. I mean, you could have perturbed it more and like, you could have come up with something that has index plus 1 and something that has index minus 1 on top of that. That's possible in general. So for example, like if you actually do, in other words, if you do a source and a saddle, then you can actually cancel them out. Okay, so anyway, so this is a constructive picture to construct the example that I wanted to construct earlier. You can also, go from here to here and kind of perturb and make this point here that's not simple into two simple zeros. And kind of the last picture I want to draw before the proof is basically the picture when you have a sink or a source and a saddle point. So if this is a source and this is a saddle, the nice thing is the following. So, if you think about this neighborhood and you want to kind of bring them together and make them collapse, you can, with a homotopy, what you can do is you can, make them collapse. And what happens is after they collapse, then you actually can find a vector field on this guy, on this set, that you can replace this by a non-zero vector field, a vector field that doesn't vanish, that doesn't have any zeros, basically by just going like this. So, this reflects the fact that the total index here is 0. And the total, so therefore, the total index here is still 0, that's compatible. That doesn't mean, the one thing you should be careful about is that doesn't mean that if the Euler characteristic is 0, it's not obvious that you can always find a non-zero vector field. Okay, that doesn't mean you can always cancel vector fields, zeros of vector fields. But at least in dimension 2, you can. Okay, so in higher dimensions, it can be a little bit more subtle. Yeah. Okay. All right, so now we can actually prove the Poncare Hop Theorem. Mm-hmm. Oui? Yeah. Uh-huh. I mean, yes, you actually can do that. I mean, when you say partition, usually people partition positive numbers into positive numbers. So there's only one partition of 2, which is 1 plus 1. But if you allow negative numbers, you can have, like I said, you could actually introduce 2 more here if you want. Like, you can write 2 as 1 plus 1 minus 1 plus 1. So yeah, you can. Yeah. But there are some restrictions on the topology. Like, for example, you can't have 2 sources. You have to have a source and a sink. But in terms of the index, you don't differentiate that. So that's why it's a little bit more subtle. But yeah, you can if you write a bunch of minus 1 plus 1 minus 1 plus 1, you can find a picture that fits that. Yeah. Okay. All right, so let's now prove the theorem. And I guess I didn't say, but the proof here that this thing holds, I mean, it's an observation. It's very similar to what we did last time. You kind of, if you want to compute the degree of the map here, you can, just put little balls around here. And, you can basically find a homotopy through non-zero vector fields that goes from here to there. And sorry, what you do is, oh, forget this. So v and v tilde are equal on this, on the ball, on the sphere, that's that over here. And the index of v, of p, of v at p, is just this degree, the degree of this map here. So the degree of the map here is going to be the same as the degree of the map v tilde over norm of v tilde over here. And now use that property that I said last time. The degree of this map here is going to be the sum of the degrees of all these maps here, because it's some intersection number that extends over a set, over a compact manifold with boundary. So this is the same calculation I did last time to prove this equality here. Is that clear? Or if you want, I can write this down. It's clear? Thumbs up? OK. All right. So if it's not clear, then maybe this is an exercise for you. And I think it's a good one. OK, so now proof of the Poncare Hop Theorem. So we may assume without loss of generality that all zeros of V are simple. OK, that's just because of this property. If we have isolated zeros, we can perturb V, and then they all become simple, and this thing is preserved. OK? OK, so now we can, we're going to define the flow. So let f of t, we want this to be the flow, the flow of the vector field V. So remember what the flow is. The flow is the unique map whose derivative at time 0 or every time is this vector field V. So this is a diffeomorphism. Ft is a diffeomorphism such that the derivative ddt of f of t at x is the vector field f of ft at x. That's what the flow is. So you have your vector field, and then you follow it for time t, and then it takes a point here to a point here. And the point is, and this is kind of not completely obvious, but it's a result from ODE that so this is well defined for every t because the manifold is compact with no boundary, and the vector field is smooth. So in particular, it's locally Lipschitz. So this is well defined, unique, blah blah blah. And one maybe not so obvious thing, but it's true, is that if epsilon is sufficiently small, then the set of fixed points of the flow of f epsilon, of ft, is equal to the zeros of v for every t between 0 and epsilon. So what is that saying? Like if it's saying that if you're not at a 0 of v, then the flow has to move you somewhere else. So the t has to be small because sometimes you can have a closed loop of a vector field. But the point is, it's kind of a simple exercise. Maybe I can leave this as an exercise if you've never seen this. But it's basically, if you start from if your vector field is non-zero at a certain point, then the time that it takes to get back to this point is bounded below. So you cannot basically, it's not completely obvious in the neighborhood of a 0. So you could kind of imagine a situation where you have little loops that have kind of smaller and smaller, smaller and smaller periods. But that's not possible. Okay, I think that's kind of the main thing I have to check, is that like near 0, you can't have little loops that have smaller and smaller periods. That doesn't lead to a smooth vector field, or that cannot come from a smooth vector field. Okay, but that's kind of an important observation. That you can actually take time t, and the flow, after time t, doesn't have any fixed points that are not zeros of the vector field. So the zeros of the vector field, the flow just doesn't do anything. It just keeps them fixed. Okay? So that's kind of an important observation. Okay, and remember what the fixed points is. I guess I didn't write this down, but that just means that the points that are not moved by the diffeomorphism. So, the fixed point set of ft, this is the set of points in X such that ft of X is equal to X. In the set of zeros, of course, this is just a set of points such that Vx equals 0. Okay? So, of course, the set of zeros is always contained in the set of fixed points. Okay. All right. So now we're going to look, we can do some intersection theory. So remember that, delta is the diagonal. So we can write it like this. This is J0 of the identity. So the 0th jet of the identity, the image of that. So this is a subset of x times x. And you can also look at the graph of f of t. So this is, the 0th jet of f of t. And also this is the set of points of the form x and ft of x for x in x. Of course, the diagonal, if you want, is the graph of f0. f0 is the identity. Okay, so that's the flow at time 0, so you don't move anything. Okay. So basically now my claim is that delta, that the diagonal is transverse to the graph of f of t, and that the index, and for each 0, so for each x a0 of v, that the index of this is the sign of the intersection. X, the intersection of the diagonal and the graph of f of t. Okay, so notice that of course a point on the intersection of the diagonal and the graph is the same as a fixed point of ft. Okay, because if I'm on the graph and then I'm also on the diagonal, so that means that ft of x is equal to x. Okay, so there's a bijection between this and the set of fixed points. So there's a bijection between this set and the set of fixed points. And what I'm saying is that, in the set of fixed points, I told you, we have t sufficiently small, so the set of fixed points is equal to the set of zeros. So for each 0, I have an intersection here that comes with a sign. It's either a +1 or a -1, because I'm assuming I'm claiming that the intersection is transverse. And the index also has a sign, and it's +1 or -1 because all the zeros are simple. Okay, so that's my claim. I guess the first thing to notice is the claim makes sense. It makes sense to say this. Okay. Now, if you believe this claim, and I guess it's not too hard to believe the claim, at least the first part, it's kind of what Marcelo was saying, you start from a vector field, you look at the flow of the vector field, and it kind of makes sense to think that the flow is, at any point that at a zero, that it's going to be transverse to the diagonal if and only if the zero is simple. That kind of makes some sense if you think about it a little bit. But I'm going to prove that in a little bit. But anyway, and then there's this question about the sign of the intersections, which is really like a linear algebra question. So that's really not so obvious, but you have to do the calculation. But anyway, let's assume the claim. If you suppose the claim, then the rest of the theorem is very easy. So if the claim is true, then that means that the sum of the indices is going to be the intersection number of delta and the graph. Right? So that means that the sum of the indices for Vx equals 0 is going to be equal to the intersection number of delta with the graph of the flow. But the graph of the flow, we can actually homotope this to the graph of f0. So by homotopy, this is equal to the intersection number of delta and the graph of f0, which is just delta again. So this is by homotopy invariance. So that is the Euler characteristic of x, by definition. Okay? And in particular, that kind of gives you a nice way, a nice example of how you compute the Euler characteristic. You can just basically pick a vector field, look at its flow, and when you look at the flow for a very small time, then it actually, the graph of that will intersect the diagonal transversely. So you can compute that intersection number, which, by this claim, by the second part of this claim, is going to be the same thing as computing the indices of the vector fields. The indices of the vector field at the different points, at the different zeros. Okay, so now I have to prove the claim. Okay, any questions before? Okay. So proof of the claim. Well, since everything is local, we can just look at the vector field as a vector field from Rn to Rn, and we can kind of do the computations in Rn. So we can look in oriented charts. So now my vector field, I can think of it as being a map that goes from the ball of radius epsilon to Rn, such that 0 is a regular value, and V inverse of 0 is just 0. Okay, 0 is the unique 0 of the vector field, and it's a regular value. So by the inverse function theorem, we might as well assume that, like I said before, you either have the identity or the reflection. Okay? So we may assume without loss of generality that V is either the identity or is a reflection. The identity will correspond to the places where the index is +1, and the reflection will correspond to the points where the index is -1. So now all we have to do is to see what happens to each of these cases, what happens to the intersection of the diagonal and the graph in each of these cases. Okay? So, well, let's look at the flow. So what's the flow of V? So the flow of V is, well, let me say that this will be, okay, let me call the sign Q. So Q is plus or minus 1. So it's going to be plus 1 in this case, and it's going to be minus 1 in this case. So V of x1 through xn, in both cases, will be Q x1, x2, xn. So I just want to write it like this so I can simplify my notation a little bit. OK, so now I can compute the flow of V. So when the vector field has such an easy expression, then the flow is very easy to compute. The flow is just the exponential. So the flow will be ft of x1 through xn is e to the qt x1, e to the t x2, e to the t xn. OK. So yeah. So now I have to look at the tangent vector field. Now I want to look at the diagonal intersected with the graph of ft. But actually, this only has one intersection in this set, which corresponds to 0, 0. So we know, this intersection in this trivialization is just has one point. So the first thing we want to show is the transversality condition at this point. So we have to look at the tangent space to delta plus the tangent space to the graph. And we have to ask whether or not this is going to be the tangent space to x times x. So this would give you the transversality condition. And then we have to check sort of the orientation of the two. We have to check that the natural orientation of these two gives you the orientation of this guy. OK? So how do we do that? So everything here is oriented already. So kind of Rn comes with the usual orientation that's given by, say, you take the canonical basis. And that's kind of the positive orientation. So if you have a basis of Rn, so if this is a basis of Rn, sorry, this x here is really Rn times Rn. So that induces the orientation of Rn times Rn, which is the following. So the induced orientation on Rn times Rn is basically the following thing. So you kind of put the first basis of the first guy, and then followed by the basis for the second guy. So using the product notation, the induced orientation on Rn times Rn is given by, choosing a basis like this. So I can write it like this: E1 times 0, etc. En times 0, and then 0 times E1, and then 0 times En. OK? All right, so that's an oriented basis of Rn times Rn. That's the usual orientation that we give on products. OK? And then, what are the induced orientations on? So what are the induced orientations on the graph? So on the graph. So on delta and the graph of ft. Well, that's going to be, basically, the induced orientation on the graph on the zero jet of a function is basically the derivative of the function. So you see the jet as a section of a bundle, and then you look at the derivative of that. So this guy you see as the zeroth jet of the identity, and this is the zeroth jet, the image of that, and this is the zeroth jet of the flow. So basically you take something that's an oriented basis here, and you push it forward by the derivative. So this guy really is, you take x to x. So an oriented, the orientation on delta would just be given by E1 times E1, E2 times E2, etc., En times En. And here, what you have is basically the induced orientation will be given by certain, and the other one will be given by E1 times the derivative of f times E1. So f is just a matrix, so the derivative is itself. So it's going to be E1 times e to the qt E1. Oops, E1 is kind of a bad letter. I just realized. But I'll leave it like this. But you know that E1 is not an exponential, and e to the qt is an exponential. I think this is the last line I'm going to write e, and then I'm going to make it into a matrix form. Anyway, so I apologize. E to the t times E2, etc. So En times e to the t times En. Okay, let me say one more time. There are two e things going on here. There's the Euclidean basis, and there's the exponential. That's a warning. That's what happens when you don't follow your notes closely. You change your mind and actually, I prefer writing the different way, and then you get stuck with this. I had V's in my notes. Okay, but anyway, what happens is, how do we know if we have two bases of, we have two subsets of Rn times Rn, how do we know if they together span the whole Rn times Rn? Well, we have exactly enough vectors to make a square matrix. So basically, the two together are going to span the whole R2n if and only if this matrix, that if you put together all these guys, if and only if this matrix has non-zero determinant. And the orientation is going to match the orientation of R2n if and only if the determinant is positive. So all you need to do is basically you put these vectors, all of these, and then followed by all of these in a matrix, and then you have to compute the determinant of that matrix, which is actually a very easy thing in this case. So when you put these guys together, so putting these, I guess these are linearly independent sets together, we obtain a matrix. So the matrix, basically you have to kind of compare these with this. So the matrix that you get from this guy is like the identity in R2n. So you have to compare sort of this matrix that you obtain by putting these two together with the identity, which is why I'm saying, just take the determinant of the matrix and show that it's positive. So that will tell you that it's transverse and that it has the right orientation. So when you put this, of course, like I said, this guy in a matrix, so you have E1, 0, E2, 0, En, 0, and then 0, E1, etc., 0, En, which is exactly the identity matrix 2n by 2n. So now you have to look at what the matrix here is. So it's not hard to see, that the matrix that you obtain is going to be the following thing. So it's going to be identity, identity. So that's E1 times E1, E2 times E2, and so forth, En times En. And then the second coordinate, the second side of the matrix, you're going to have identity. And here you have e to the qt, e to the t, e to the t. Okay, so what's the determinant of this? well, so this is the matrix, and whose determinant is equal to what? Can you see? Well, first, you do a little transformation. The determinant is going to be the same as the determinant of the matrix identity, and then you can take this line and subtract from here to make this into a upper triangular matrix. So you have 0 here, and then you have e to the qt minus 1, e to the t minus 1, e to the t minus 1. Okay, so this determinant is now going to be e to the qt minus 1 times e to the t minus 1 to the n minus 1. All right. So t is greater than 0. So this part here is always positive. And this part here, t is greater than 0, but q could be plus or minus 1. So this part here is going to be always non-zero, but it's going to be plus 1 if q is positive and minus 1 if q is negative. So the thing is, the sign of this determinant is going to be the same as the sign of q. So this, so the sign So I guess, first of all, this is always non-zero, which means that the intersection is transverse. So first of all, the determinant is always non-zero, which means that the intersection is transverse at 0, 0, which is the only place where they intersect in this little neighborhood, where I trivialized everything. And second, this determinant is positive if q is positive, or I guess if q is plus 1, and the determinant is negative if q is minus 1. So the determinant will tell you exactly what the sign of the intersection is, as we defined earlier last week. The sign of the intersection is exactly, it's going to be plus 1 if this is well-oriented, so the orientation of this guy matched with, put together with the orientation of this guy, gives you the orientation of this guy. And it's going to be negative if you have the opposite orientation. So that's the same as computing the determinant and determining if it's positive or negative. So the conclusion, so this is basically the end of the proof of the claim. So this concludes the proof of the claim. Okay? So the sign of this intersection, which is 0, 0, is the same as the sign of the 0. So it's, it's either a plus 1 or a minus 1 because it's a simple 0. So then the signs match. Okay? So that means, let me go back to how you prove the theorem using the claim. So that means that the sum of the indices of all the zeros is going to be the sum of the intersection, so the count of intersections with signs, which is the intersection number. So that's going to be the total intersection number of the diagonal with the graph of the flow. And since the flow is homotopic to the zero flow, then you can bring it all the way to 0 in the graph of the zero flow. The zero flow is the identity. That's just the diagonal again. So yeah, so I guess I can write this down one more time. So by the claim, the sum of the indices, so this is just the intersection of delta with the graph. So you do this, for every, the claim shows that this index is going to be exactly the same as the sign of each intersection. So you have this. So by homotopy invariance, you have that this is equal to this, which is the Euler characteristic of X. Okay, so that's the end of the proof. Okay, are there any questions, comments? Okay, so now I want to finish by talking a little bit about the Lefschetz fixed point theorem. That's another theorem that's very similar. It's kind of a generalization of the Poncare Hop theorem in a sense. But as I stated, it will seem like a very trivial theorem. But I guess the understanding of the theorem is maybe kind of non-trivial. But a lot of things, if you state it the right way, then they're trivial. So it seems like empty of content, but it's not, as you'll see. So the Lefschetz fixed point theorem. So suppose that suppose X is a compact oriented manifold with no boundary. And take a function that goes from X to X that's smooth. Then we can define what's called the Lefschetz number. The Lefschetz number, there are different ways to define it, and I guess that's where that's where we can say that the map that's when you can say that the theorem is trivial or not, is depending on how you define the Lefschetz number. But I'm going to define it in kind of a way that's going to make the theorem trivial. But here it is. So this is the way you can define it using intersection theory. So this is the intersection of delta with the graph of F. This intersection number in the diagonal space, in the product space. Okay? So the theorem says the following. If the Lefschetz number is different from 0, then F has a fixed point. Okay, so that's kind of the classical, it's a pretty old theorem, very classical. And I guess the real insight here is a definition of the Lefschetz fixed point, the Lefschetz index in terms of the intersection. So this is called the Lefschetz index. Okay? I mean, the proof is basically one line. I don't know if it's even worth writing, but okay, let's write it. So how do you prove that? Well, if F does not have a fixed point, so a fixed point is the same as an intersection point of the diagonal with the graph. So if F does not have a fixed point, doesn't have a fixed point, then the intersection of the diagonal and the graph of F is empty. So this number is 0. Is the intersection is 0. And there we go. So, that's, I said, if you state it like this, it's completely trivial. I guess what's kind of interesting is that historically, this has not been the definition. So you can define it in other ways. And let me tell you another way to define it. And I guess, I'll leave as an exercise to show that these two are the same. So we start, in the case where, so if the graph of F intersects delta transversely, then we define the following thing. Then then for every intersection point, if you take an intersection point, you can look at, you can define a local, then for each intersection point, you can define a local Lefschetz number. Sorry, it's not ft, it's f. Now f can be any map from x to x. You can define the following thing. So this this is the sign of this intersection, of the intersection point. Okay, so this guy is an intersection point of a transverse intersection. So it comes with a sign. So it's either plus or minus. So it's either plus 1 or minus 1. So you can define this to be, this number. So because basically the definition of the Lefschetz number. So far I'm actually not going to do very much. I'm going to just say that this is the sum of Lxf for all the fixed points. Okay, so far this is kind of completely trivial. I'm just saying if you're transverse, then the total intersection number is the sum of the signs of the intersections. But I guess the thing that is actually interesting, and maybe this is what the exercise should be, is that this Lefschetz number is the sign of the determinant of df x minus I. So if x is a fixed point that is where this intersection is transverse, that will imply that's actually equivalent to saying that the derivative of x minus the identity is invertible. So since everything's oriented, this actually has a sign. This determinant has a sign. The value of the determinant depends on the charts, but the determinant has a sign. So you can, another way to say is just if whether this transformation here, which is an invertible transformation, preserves the orientation or reverses the orientation. Okay, and this is not very different from what I did in this case. So I guess it's not so hard to see that. You can think of the Poncare Hop Theorem as a corollary of the Lefschetz fixed point theorem. Or at least a corollary of these calculations here. Because you can just take the function to be the flow of a vector field. And this calculation here is very much the same, very similar to the calculation that I did here. You took your flow, the derivative of the flow. In our case, the flow was just a linear thing. Just multiplying by a matrix, the derivative was the matrix itself. And then we ended up with the determinant of the matrix minus I. So that's exactly what we got here. Okay? So anyway, so I guess if you defined the Lefschetz number like this, then you would have a kind of a non-trivial theorem. But of course, you have to extend this definition to the case when f is not transverse to the diagonal. Otherwise, again, the theorem is kind of obvious, because if you know that the intersection is non-empty, then you have a fixed point. So I guess the real theorem, I think the theorem that's more interesting. The reason I'm not concentrating so much on the Lefschetz fixed point theorem is I think it's more interesting when you define it in homology, like for homology. So kind of if you define it as the sum of the traces of the derivative of f, or the push forward map in homology for all the homology groups with signs. So because we're not covering algebraic topology here, we're not covering homology groups. I don't think that I want to say that much more about the Lefschetz fixed point theorem. But I guess this exercise, it's done in Gilliam and Pollack, and I think it's really a nice little like ODE / real analysis exercise. Not much harder than this. Okay, I guess once you see this, it's kind of not so hard to believe that. You put them. You just kind of put the basis kind of in the same way, and you kind of get this. Okay. So I think I'm gonna stop here for now, and we'll continue later today. Okay.